Hi everyone. In the previous video, we worked on example 4 using an ice table, and we saw that we had to use the quadratic equation or the quadratic formula to solve for x. The quadratic formula usually gives two values for x, and we have to evaluate those two values to figure out which one made sense and which one we can reject. Now that quadratic formula and plugging in the numbers and solving for x was a pretty drawn out process. So in this video, I want to discuss an approximation called x is small that would help us avoid having to use the quadratic formula for some, not all, of the ice tables that use the quadratic formula. Now I will introduce this problem number 5 or example number 5. I may not be able to do it all. If I don't have time, I will do all of example 5 in the next video, but I do plan to introduce this problem where we can use the x is small approximation. Let me just remind us what example number 4 was all about. We'll call this part A. And example number 4 gave us initial concentrations for all three molecules in the chemical reaction. And the Kc is above 1, it was 54.3. I won't show you all the work that we did to solve for this problem, but the first step, as usual, is to determine which side the equilibrium will lie on, or which side the direction the reaction will go to. So based on QC, I think we decided that the reaction will mainly go to the left. The rate of the reverse is now greater than the rate of the forward. And that's because, we do have a lot of the product, and QC was greater than KC, greater than 54.3. And then we constructed our ice table. Again, I'm not showing you all the work. You could go back to the previous video if you want to see exactly how we did this. And for part 3, you write out the equilibrium expression and plug in the numbers. So there's our formula to solve for x. And when we expanded the numerator and denominator, and we put every term on the one side and 0 on the other side, we get this. This is the form of a quadratic equation, and we're going to use the quadratic formula or the quadratic equation. Again, you're setting it all to 0, and you have a value for x squared, a value for x, and the c value. So the quadratic equation is on the right, and we solve for x. And we got two values for x. You get two values because, see, this is a plus and a minus. You do both of them individually, and you get these two values, and it doesn't make sense for us to have a molarity that's negative. So we will be using, or we use this x to figure out the equilibrium concentrations for all the components of the reaction. Okay, and we finally got an answer for the concentration of H2, concentration of I2, and the concentration of HI by plugging in this x here. Now, what is this x is small approximation? It's going to allow us to avoid using the quadratic equation. It simplifies the whole process. Now, there are very strict rules as when to use the x is small approximation and how to double check if our use of it is valid. This is part B, x is small approximation. Literally, when I do this on paper, I put the quotes always, x is small approximation, meaning that we're going to prove for some cases not all cases, but for some cases, we could assume that x is so small that it is 0. And I'll show you ways to figure out whether that is true or not. Number 1, you could ignore a plus x or a minus x term, or even a plus 2x or a minus 2x, etc. But that's if the term is not squared or raised to a power. This is going to be pretty long. Us writing down all the requirements to use x is small, but when you use it in practice, it's pretty simple. And again, I will show you that for example number 5. Number 2. Oh, no. I didn't even finish my thought for number 1. You could ignore plus x minus x, etc. if x is less than 5% of the initial concentration. Now, you could have different initial concentrations if you have more than one reactant. You will have to double check whether that x is less than 5% for each of those reactants. Again, this will make a lot more sense once we apply it. Number 2, it's analogous. Let me give you a picture. It's analogous to weighing yourself on a scale. And then weighing yourself holding a quarter, the coin. This quarter is the x. It's essentially 0 when you compare it to the weight of your body. So when we add x, or the weight of the quarter, again, we can ignore it. It's definitely less than 5% of your body weight. We can ignore it, and it's valid, and whatever answer you get for your body weight or your x will be correct, or would be what do you call it? It would be considered correct. It allows you to avoid the quadratic formula. Basically, that's why we're using x is small. I want to warn you, if you can get to x without using quadratic formula, like in examples 1, 2, and 3 in the previous videos, you cannot use this approximation. This is strictly just to avoid using the quadratic formula. Number 4. What is number 4? Oh, after you find x in the equation, you have to double check whether that x is less than 5% of the initial concentration. You have to do the check. So once you do get a value for x, so that I think some people are misunderstanding. Well, we're not eliminating x altogether. You got to have x in your expression somewhere. This approximation is getting rid of any x where we do a plus or a minus. And I think that will be a little more apparent once we do one example together. Example number 5. So once you do get a value for x, okay, you will check. And for my students, you have to show the check. You have to double check and prove that it is 5% of the initial concentration, less than. I think, what time is it? I think we'll have time to do some of example 5, and then I'll stop the video, let you work on it, and then you can come back for the next video to see how I would do all of example number 5. Anyway, we do the double check. And then number 5, I had one more. Oh, let me give you a rule of thumb. I don't want my students to, be confused when or when not to use the x is small approximation. Rule of thumb. If k, I should just say kc first. If the equilibrium constant kc or kp is 10 to the minus 4 or smaller, and you are using the quadratic formula, so there are two requirements. If kc or kp is 1 times 10 to the minus 4 or smaller, and it looks like you would need to use quadratic, then definitely try using or use the x is small approximation. But you would have to, at the end, double check and prove that this is valid. So at the end, prove x is small. And I like to give my graders, if I was taking the test, I would give my graders a very clear answer that it's valid, if it's valid. Okay, if it's less than 5%. If it's more than 5%, then unfortunately you will have to use a quadratic formula just like we did here. For example, number 4. Are we ready to look at that problem? Example number 5. I'll give you a couple clues and show you why we're going to use the x is small approximation, but the whole problem may not be on this video. It may be on the next video. So here it is, example number 5. For us, this is part C. Okay. The reaction shown is known to have a Kc of 3.39 times 10 to the minus 12. So that's a good indication that we might be using the x is small approximation because the Kc is 10 to the minus 4 or smaller. What will the equilibrium concentration be for atomic iodine? Okay, look at your equation. Atomic iodine is this right here. So this is question mark. And this is the molarity at equilibrium. And honestly, we get the molarity at equilibrium for both of these. But your data is not giving you molarity. They're giving you a moles of molecular iodine. So that's molecular. That's atomic. And they give you the volume of the flask. Okay, the first thing to realize is that, number one, we have no product, right? They're putting molecular iodine in a flask, they're sealing it, and then they're letting it equilibrate. So there's no product initially. So QC is less than KC. Okay, but what's more important is that when you do that plus X minus X for the change row, you are adding to the atomic iodine and you're subtracting from the molecular iodine. So the main um, the main conclusion for number one, part one, is that the rate of the forward is greater than the rate of the reverse. Right? It's not at equilibrium. So the rates are not equal. One will be bigger than the other. Number two, ice table. Okay. Very simple equation. I2 goes to 2i. We do have a coefficient 2. So eventually in the expression we'll have to square that concentration. But let's do the ice. And, so I've tried to emphasize in the past when you do an ice table, really try to only use molarity or the partial pressure of a gas in atmospheres. Okay, so we have molarity. We actually don't have molarity. We have the moles of I2, but to get the concentration, it's moles per liter. So we are using the volume of the flask. Okay, so that would count as a concentration for a gas. What is the mass per volume? 0.0031 divided by 2. Okay, so that is a molarity for a gas. 0.00155, and I'll put here m. You don't have to, but I like to remind myself that I am using molarities. This is 0. So again, from step 1, we said the rate of the forward equals rate of the reverse. So we are definitely losing reactants and making more products. So your minus x is here, and your plus x is here, but you have a coefficient of 2. Remember how I like to think of explicitly putting 1 here? And that is what x? Well, we have a 2 here. So that's why we're going to multiply by 2. So we're adding 2x. And that makes sense because for every molarity of I2 I lose, I gain 2 molarity units of x. Equilibrium, 0.00155 minus x. And then here we have 2x. Am I doing this whole problem? Why don't I stop there? Let me think if I should stop there. I'm going to stop there, and I'm going to remind you that for number 3, you will write out the Kc expression. Because Kc equals 3.39 times 10 to the minus 12, you will ignore any plus x or minus x. Typically it's going to be one of those. Sometimes there will be a plus 2x minus 2x, but let's not worry about that here. Honestly, boy, I'm very erratic. Let me do this problem. Why not? We have time. Kc equals concentration of I atomic squared. Okay, that's coming from your reaction. Okay, products over reactants, but raised to the power of the coefficient. And then concentration of I2 equals. Okay, so it does equal a very small number. And what is I? I is 2x. So this equals 2x squared. Oops. Does everyone know why this is incorrect? It's that squared, the 2x squared, not just the x. So you do need to show parentheses. And we have this 0.00155 minus x. In the margins, I'm going to write for the greater, we are going to use x is small. And I'm going to get rid of x. It's analogous. We have our body weight, and here we're subtracting a quarter. So how about we weigh ourselves, with a bunch of change in our pockets, and then we weigh ourselves again but we remove one of the quarters that was in our pockets. Essentially, it's the same weight because that quarter is so small compared to our body weight. We're going to have to double check that. Okay, we'll solve for an x, and then we'll do the 5% rule. So what do you notice here? This one you keep. It's not a plus x or a minus x, so you keep this x. And that's how we're going to get a value for x to plug in to the equilibrium row. So now we just have to solve. So that x is gone. Think of it as 0. So let me just write it out, and it's very clear what we're solving for now. 0.00155. Okay. So on the right-hand side, this is 4x squared. Now the x is squared, and I've squared the 2 already. 3.39 times 10 to the minus 12 times 0.00155. 155. Okay. 5.2545 times 10 to the minus 15. Okay. I have that number saved. I divide by 4, and then I take the square root of that answer to get x. Let me get to scientific notation, and it's pretty tiny. 3.62 times 10 to the minus 8, and that is the molarity, equals x. And we're going to plug that number up here. Okay. Okay, so there are a couple things. We're not quite done, but we did the hard part. The first thing is we want to check. Okay, so here's my check. It has to be less than 5% of the original. So literally you're just doing this. 3.62 times 10 to the minus 8 divided by the original. And that has to be less than 5%. Remember, for a percent, you are multiplying by 100. Good, I have that number saved. Divided by 0.00155 times 100. And let me get out of scientific notation. And it's low. It's 0.0023. And that's after I multiplied by 100. So this is the percent. So again, I'm going to tell my grader x is small. Valid. It is fine that we use the x is small shortcut or the approximation. Now, here's another issue. In the solving of x, I said this is essentially 0. But after you find x and you plug it into here, you're literally going to use the x that we found and plug it back. Okay? You're not going to think of this as 0 anymore. All right? So the concentration of I2, I mean, it might essentially be the same, but you just want to prove it. 0.00155 minus, 3.62 times 10 to the minus 8. That is what, 7 zeros? Okay, but we could formally do it. 0.00155 minus 3.62 times 10 to the minus 8, and yeah, see, when you round, it's essentially the same thing. 0.0015, yeah, 1550 molar. That is the concentration of I2. Now, yes, it does look like it didn't change, but we're still going to get a change for atomic iodine. We're going to get X, and we're going to multiply it by 2. So let's just multiply that by 2. 3 point, which one? This by 2, right? 3.62 times 10 to the minus 8 times 2, scientific notation. So we do get a little bit, and you do have to show that some of the product was produced. And you are going to give a number, even if when rounding, there is no I2 lost. There was, for sure. It's just that it's so small that you don't see it in the final answer. But for atomic iodine, go ahead and put exactly what you get when you plug it back into the equation, when you plug X back into the equation. Okay, so that 7.24 times 10 to the minus 8 is coming from 2 times X. And again, we solve for X over here. Let me zoom out. It is still a bit of work, but by doing this by removing this minus X, we avoid the quadratic equation. We avoid having to expand everything in solving for X using the quadratic formula. And we also made sure that we validated that approximation. That is definitely less than 5% of the original concentration. Okay. Practice, practice, practice. Again, you should never be at a point where you eliminate every X. You got to solve for an X somehow. It's going to, most cases, it is going to work out very similar to what we did here. The last warning that I'll give, and then I'll get off this video, is that you don't use this X is small for everything. In our previous examples, and I have one here, over here, you don't get rid of this X, because you could solve for X very simply by taking the square root of every term. So again, this X is small approximation is if you think you're headed towards having to use a quadratic, and we were. We would have had to use a quadratic if we didn't get rid of this minus X.